Test May 6, 2024, that's physics 7. And here how the schedule, our schedule is going. Today is Monday, right? And we finished chapter 25. We started chapter 26, which is refraction. This is the third meeting of refraction. Don't forget, our exam is going to be next week, 9 days from now. Okay, so we cover, since the last exam, we covered chapter 22, 23, 24, and 25. And I expect that we can finish chapter 26 before the exam. Let's keep this way for now, okay? So chapters 22 to 26. And let's take a look at the notes. This one is this one here, okay? So here you go. Here's a list of the chapters since 22, right? In chapter 23, we had to go back to chapter 20, so we can we start talking about alternating circuits. Okay, we are not gonna cover resonance in AI. Okay. May or may not, we haven't covered this one, and this one definitely we're going to cover. I don't think there will be time to cover this one here, resonance in electric circuit. So we cover all those chapters here. 24. Oh. And then we started geometrical optics. Geometrical optics start on chapter 24 with mirrors. Okay. Skip it for now. Let me put it here. Skip it. Skip it for now. Let's look this way here. And we finished chapter 25, 1, 2, 3, 4, 5, 6. And then we started on chapter 26. I covered everything in bold phase so far. And now we are going to start this chapter here, spherical lenses. And then formation of image by lenses and seeing lenses. Hopefully we'll be able to do that. That's the bulk of chapter 26. Okay, that's the bulk of chapter 26. And then we can, if you have time, we're going to cover everything else here. But for a must for this chapter are those bold-faced sections here that you see. Okay, we talk about index of refraction, right? There is Snell's law, total internal reflection as well, and dispersion of light. That's what we did. Then we had the lab last week, right? And that's what we're doing right now. Spherical lenses. Okay, so what we're going to do, here you go. In this chapter, we will introduce the very basic ideas of a seeing lens, of seeing lenses. Okay, seeing, and it's not just seeing lenses, but it's seeing spherical lenses. Okay. And the definition of seeing, right? The definition of seeing let's put it this way, seeing is defined is defined in terms of the diameter of the lens. Okay.
Professor, can you share your screen?
Oh, yeah, thank you, thank you. Let's see here. Okay, here. Sorry. Yeah,
Thank
so
you.
let me just repeat what I just said, right? Oh, going back here to the, not this one. Yeah, I don't want this one. I want the other one here. Okay, so let's just repeat what I said, right? So here you go, today is Monday, right? Then don't forget the exam is going to be next week. I will bold face it here so you can remember that. We are starting the third part of refraction. And here are the notes. Here we have all the chapters we have so far for the third exam. Chapter 22, chapter 23, and we also went back to chapter 20 because I want to cover AC circuits in a single stroke, right? So for some reason the book put this alternating circuit in chapter 20. I wouldn't do that. Okay, then we talked about electromagnetic waves, chapter 24. Polarization, we are skipping polarization so far. Skip. I'm gonna boldface it here. Okay, we're skipping this one as well, the Doppler effect. Okay, and we will, once we get into special relativity, let's see, we'll go back to this one. Section 25 is the first section, chapter 25 is the first section on geometrical optics. Geometrical optics 1, right? The theory of geometrical optics is the easiest theory that we will ever see for light. Okay, and wavefronts, mirror equation, and then we started covering refraction, chapter 26. Everything in boldface here is what I'm planning to cover, at least, right, in this chapter. Everything in boldface. And moving forward, that's the, you go. Okay, seeing lens, the theory of seeing lens, the theory of seeing spherical lenses is a very good approximation for real life lenses. Very good approximation. Okay. So let's say seeing lens, the thickness of the lens must be much less than the diameter of the lens. Okay. So thin, I'm gonna put CNT. The instead of the diameter, D of the lens. Okay. So if you have this relationship, this theory approaches explain very well the behavior of the lens. Now, very important, the theory that we're going to present here, although a little bit more involved, it is very similar to the one that we cover for spherical mirrors. Although, although it is a little bit more involved. Little bit more involved. Sky is coming. The device is different, light behaves differently, but the final formulas are going to be exactly the same. Okay? That's an amazing thing. Even though we have two different devices, one with the mirror, the other is the lenses, the light behaves, the equations that we use for them are exactly the same. Exactly the same because we are using a thin lens. The first thing that you have to know is the existence of collimated rays, parallel light rays. And parallel light rays or collimated light rays are created from objects that are very far away from the lens or the mirror, like the moon, for instance. The light rays of the sun, for instance, it had to be parallel to the principal axis of your lens or mirror. The light rays of the stars as well, and the moon, etc. Okay? That's how we can create, but there are other ways too. Okay, that's the further away an object is, an object that emits light is, the closer its light rays will be to a collimated light ray. So the further a light source is from you, okay, the closer, the more collimated, let's say, the more collimated its light ray will be. That's what you have to know. And there are also, and how do you judge whether an object is very far away or not? Okay, so we judge that in terms of the focal distance. Okay, the distance of the object must be much greater than the focal distance of the lens or mirror. By the same token that a mirror has a focal distance, a lens also has a focal distance. And we can approximate that to 10 times the focal distance. If this condition is satisfied, we can state that the light rays are almost parallel to the principal axis of the optical device. Okay? And we have different types of lenses. Okay, here you go. We have different types of lenses. Okay, we have planar convex lenses. Okay? This lens here is said to be positive. We have planar concave lenses. This type of lens is said to be negative. We have biconvex lenses. And you're going to see very soon. In this case, the lens is also going to be positive. We have biconcave lens, which will always be negative. And you have everything else in between. We can, let's say, biconcave. I can do even better than that. We have convex, concave, concave, convex, concave, convex lenses. Someone is coming in. Okay. Convex lenses can be either positive, or negative. I'm going to tell you exactly what that means to be a positive or negative lens. Now is at the time that we can start looking at the illustrations, okay? View, will, grid line, good. Seeing spherical lenses. So how do we manufacture as a seen spherical lens? Also, how do we illustrate a seen spherical lens, right? Okay, we create a surface, a spherical surface. That's what we do. A spherical surface of radius r, for instance. And, suppose that we have a piece of glass, okay? And we can create this curvature in the piece of glass. There are techniques that we use to do something like that. They teach it in the school, in technical school, how to do those things. Okay, and this lens right in here, the surface of this lens is going to be convex. And if I add another surface, a planar surface, now we have a planar convex lens. Okay? The radius of curvature of this surface is r, whereas the radius of curvature of this other surface, the planar surface, is going to be infinitely long. Okay? I can shape format, insert. I want to put an equation right in here. Here you go. In this case, the radius of the lens will be going to infinity because we have a planar surface. Okay, a planar surface is nothing but a spherical surface of radius of curvature, of infinite radius of curvature. That's what a planar surface is all about. Grid line, let's see, this guy here is twisted, right? That's the radius of curvature of this surface right here. Okay, so here you go, plane convex lens. Make it look nicer now. That's what it is. And then what we do to find out the position of an image of a lens formed by an image? Well, we do exactly what we did before for the mirror. We introduce the principal axis of the lens. And if we have a collimated light ray incident on this lens, what's going to happen? Remember, we have this angle of incidence here is 0 degrees with respect to the normal because we have a planar surface, and on the top of that we have a collimated light ray. So whenever this collimated light ray is incident at this angle with respect to the planar surface, it will refract without any change in the direction, right? And then when it reaches the other surface, the spherical surface, the light ray will refract into the air and away from the normal because it's going from the a higher index of refraction to a smaller index of refraction. Okay? In the next slide, you're going to see the plane that tangent to that point of the lens is a plane. By the same token that the lens is a section of a sphere, right? Of a spherical surface, of a spherical glassy surface. And now that we have the plane tangent to that point, we can draw the normal to the tangent plane. And what we do next? We do something that we do not do for mirrors. Okay? We draw what I call it the go-through light ray. We do that just for reference, okay? Suppose that there was no refraction whatsoever due to this lens. So this light ray would go through. But I'm doing that only for reference because the actual refracted light will move away from the normal. From the normal and also from the go-through ray, right? And what we have here, you know, what's going to happen? This light ray is going to cross this axis, right? The principal axis of the lens. And this point where the light ray crosses the principal axis of the lens is a special point that you should remember, right? Just like we had for mirrors, this point is called the focal point of the lens. Okay, and if you have another light ray, another collimated light ray, this light ray will also refract towards the focal point of the lens. Okay, so we now have this important point of the lens. Let's repeat that, how it works, right? So we're talking about the spherical scene, spherical lenses. Okay, a spherical lens is made up of a spherical surface, a section of a spherical surface. In this case, radius r. And let's start with the simplest type of positive lens, which is the planar convex lens. The surface is convex, the surface is planar. The convex surface has a radius of curvature r. The planar surface has a radius of curvature infinite. Here you go, planar convex lens. We're going to play with the thing, try to predict how images are going to be formed, just like we did for mirrors. So we are going to need the principal axis of the lens. Just repeating it what I did before. We're going to need, for instance, a light ray that's a collimated light ray parallel to the principal axis. And this collimated light ray is going to be refracted towards the focal point of the lens, focal point F of the lens. Okay? Just like we do with mirrors, right? A spherical mirror reflects a collimated light ray towards its focal point as well. And then I have a second here, a second light ray that's being refracted towards the focal point as well. Okay, when we are doing problems, when we are solving problems, we don't do all this drawing that we see, okay? I'm showing all these drawings so you can understand how the light ray behaves inside the lens itself and outside the lens itself, okay? But instead of doing all this fancy drawing, we do something much simpler than that. We illustrate a lens as a two-pointed arrow. That's the illustration of a lens. Actually, that's the illustration of a convex lens. Of a convex lens, a positive lens. And then we repeat exactly what we did for the other type of lens that you saw, right? Here you go. Positive lens, axis, principal axis of the lens, focal point, and then we have this F prime focal point. The image of the focal point, let's say the image of the focal point. We are going to need this second. That's something that you don't have in mirrors, right? But you're going to need this point here in front of the lens to start building the image formed by an object that is a given distance from the lens. And the procedure is very similar to what we do for mirrors, okay? First, you get the first light ray that you get is going to be parallel to the principal axis. And the light ray that's parallel to principal axis, you already know that's refracted towards the focal point. Let's do that. We go behave of light rays behavior. Even better, refraction of light rays through a lens. Okay? But even better, just like a mirror, comma, a lens also has a focal point F. And another focal point F behind the lens, behind the lens. However, unlike a mirror, a lens is also said to have a second focal point F prime in front of the lens. Refraction of light rays through a lens. 1. Collimated light rays, which are parallel to the principal axis of the lens, are refracted towards the focal point. Okay? That's my first light ray. And then we're going to need a second light ray to determine the point where the image of this object is going to be formed. Okay, so light rays that pass through the second focal point F prime is refracted parallel to the principal axis of the lens. Okay, if parallel light rays is refracted towards the focal point, light ray that passes through the focal point are going to be refracted parallel to the light ray. Did you notice that this light ray is being converging? That's what this lens do. That's what this type of lens does. Okay, that's a positive lens. It make a light ray to converge. Okay, here this light ray is being converging. This light ray is also converging towards a given point. And now that we have at least 2 light rays, we can illustrate the position of the image. Okay? Just like in the case of a mirror, the image is inverted. So there are very nice parallels between a positive lens and between lenses and mirrors. We can go ahead and draw a third light ray, a light ray that passes through the center of the lens. A light ray that passes through the center of the lens does not refract at all. Okay? So if I do everything right, the point of intersection of this light ray should be the same as the point of intersection of the other 2 light rays. And now we have everything that you need. Here you go. D naught is the distance of the object. Object O. On the other side, the image I is formed. And the distance of the image is DI. Okay? Here is the focal distance. There is the focal point, and then there is the focal distance, right? And let's go back to our drawings. Here you go. How we find the position of the image of an object due to a lens, right? Focal limited light rays are refracted toward the focal point. Light rays that passes through the second focal point F prime are refracted parallel to the principal axis. Okay. And 3, light rays incident at the center of the lens are not refracted at all. In other words, they pass through without any change in direction. Okay. Using all these, you can use all this. You can use all these 3 light rays to determine geometrically the position of the image, of an image, right? Of an image. So I'm going to summarize here. I'm going to come up with a table that compares mirrors and lenses. Okay. Thin lens. Thickness of the lens is much smaller than the diameter of the lens. Thickness T. Much more than the diameter D of the lens. In other words, and then here you go. Comparison between mirrors and lenses. We have concave mirrors, right? You already know that a concave mirror concentrates parallel light rays. And a convex mirror diverge parallel light rays. You already know that. Focal point is in front of the mirror with respect to the object. How does it compare to the lens? Okay. How does it compare to the lens? A convex lens concentrates parallel light rays, right? I'm going to put that in the same color. Right here. We didn't cover concave lenses yet. We didn't cover concave lenses yet. But you're going to see that just like convex mirrors, I'm going to put a different color here, right? They diverge parallel light rays. Even better, collimated light rays. It's better this way. Right? Here you go. Collimated, collimated, collimated. Now, if the focal point of the mirror is in front of the mirror, the focal point of the lens is behind the lens. Second focal point, let's put another one here. Second focal point. No. Yes. Right? So that's a nice table that compare the mirror with the lens. So going back here, right? Yeah. Now, what if this object gets closer to the lens? What if this object ends up sitting exactly at the second focal point of my lens, right? Well, we get something similar to what we get for the mirrors. The light rays end up being parallel, and the image is said to be improper. Okay, so you can write that down. Here you go. If an object is far away from the second focal point f prime, comma, the image formed will be real and inverted. Okay? Real and inverted. Whether it's going to be magnified or not is going to depend of the distance of the object. Okay? Now, if an object sits at the second focal point, the image will be, we call it improper. There will be, in other words, there will be no image formed because the light rays do not intersect each other. Okay. And that's what I'm doing exactly. Oh, that's what this one is. Let's see here. I'm going to elaborate a little bit more here. Here you go. Real image formed by a spherical lens. Improper image formed by a spherical lens. By a spherical lens. Here you go. And then the next one is going to be three types of images, right? Real, improper, and virtual image formed by a spherical lens. So if we move the object a little bit more to the right, now the image will be formed in front of the lens. And how do we do that? Okay, here you go. Here's the first refracted light ray, right? It passes through unrefracted. Here is the light ray that's parallel, the collimated light ray that's parallel to the axis, principal axis, is converged towards the focal point. And then here's the third light ray that passes through the front focal point. Okay, it's converged parallel to the axis. At the right side, all those three light rays are diverging from each other, right? So what does it mean? It means that the image must be formed in front of the lens. And the image becomes a virtual image. Okay? So we can go for the next one. If an object is between the focal point f prime the second focal point f prime and the lens, the image is formed in front of the mirror. It's formed behind mirror, no, the lens. Here is going to be behind the lens, and it will be real and inverted. If an object sits, the image formed will be improper. If an object is between the second focal point and the lens, the image is formed in front of the mirror, and it will be virtual and straight. This is the principle. This is the principle of the magnifying glass. In this case, the image will be larger than the object. In other words, magnification will be greater than 1. Okay? Magnification m will be greater than 1, or m greater than 1. Okay, that's for a positive lens. Now let's concentrate on negative lenses. 938. Let me put that with another. Okay, let's leave it this way. Now let's see how this thing can be worked out using a negative lens, a concave lens. By a convex spherical lens. Let's put it this way. Image, instead of real image, let's put image formed by yeah, let's leave it. Yeah, let's leave it this way. Real image. Here, improper image by a convex. Even better, positive. Positive would be better. Instead of convex, we say positive. Positive. Virtual image formed by a positive spherical lens. Now we repeat for the same thing for this other one. You know, negative lenses are much easier to treat. Okay. Negative spherical lens. Spherical lenses. Here's the illustration of a negative lens. Let's do step by step, right? So you do not get confused here. So we start with the negative lens first. And then we add the principal axis of the lens. Yeah. In the next step, we illustrate the focal points of the lens. But because this is a negative lens, the focal point F must be in front of the lens. See that? Whereas the second focal point is going to be behind the lens. Did you notice the difference here? Okay. I'm going to compare it. Let me show the comparison. Yeah, this one here. Okay, I'm going to switch back and forth. Here you go. Back and forth. Negative, positive, negative, positive. F prime on the left, F in the right. But the other is F on the left. Oh, let's see here. I want to switch this one here. Yeah, back and forth here. Right? If for a positive lens, F prime is in the left. For a negative lens, F prime is on the right. Okay? And now we can start, can do the second, we can put a object in front of our lens. In this case, the object, I put the object between the focal point F prime and the lens itself. Okay? And we go ahead, do exactly what we did before, right? Here you go. Light rays, parallel. Oh, not this one. What am I doing here? There's something strange here. Yeah, okay, this one goes away. And this one goes away too. Okay. Focal point, what I want to do, I want to copy this one and I want to paste it here. And then we add the light ray. Not the light ray, we add the object because we didn't add the object yet. We add the object right here. Right? Light rays parallel to the principal axis ends up diverging by the negative lens. If we want to find out the position of the image, we're going to need another light ray. So let's use this light ray here. Yeah? Light ray that goes through the center of the lens, refracts, goes through unrefracted. Goes through unrefracted because the lens is very thin. Okay? If I want, and let's go one more light ray here, just for redundancy's sake, right? Light rays that pass through the front focal point what happened here? Oh, interesting. See here. Yeah. I don't need that. What I need is this one. Oh, that's the extension of this light ray. So let's see. The third light ray is this one, folks. Sorry, we're too early for this one here. The third light ray is this one right here. Okay. So this light ray that pass through the focal point F prime, okay, is going to be collimated. On the right side, we have just light rays that are diverging from each other. In order to find out the position of the image, then we have to extend those light rays to the left, right? The red light ray will be extended backwards. This light ray doesn't refract at all, and then this one also needs to be extended backwards, like that. And now we have all those points are converging towards the same position. That's where the image is formed. Okay? That's where the image is formed. And you got that all the time, no matter what's the position of the object with respect to this lens. If the object is also to further away from the focal point, you're still gonna get this image that's gonna be virtual. Okay? And we have simulations, 9:48. We're gonna go for our break very soon. Okay, simulation of a lens of lenses. Let's see, optical simulation. Let's see, optical lens design, geometrical optics. Let's check this one here. Oh yeah, here you go. Okay. Here's a positive lens, right? And look what happens, right? An object, the focal point is 4 units. Further away from the lens, the image is going to be real, but inverted. Magnification is going to be less than 1. As you get closer and closer to the focal point, okay, at the point of twice the focal point, the size of the image is the same as the size of the object. As we approach the focal point passes the twice the value of the focal point, then the image starts to increase in size until you reach the focal point here. The image becomes improper. Past the focal point, you get the idea? Here you go. The image is going to be virtual. And okay, here you go. Here's the image right in here, showing up finally. You know, the object will, the image is being formed so far away that doesn't fit in this in the screen, right? But as we approach the object to the mirror, here you go. Here's the image. We have this magnification effect, and that's how a magnifying glass works. That's for a positive lens. Okay. The closer you get to the lens, the closer the size of the image becomes to that of the object. Okay, and now let's see if I can come up with a negative lens here. Let's see here, no. Yeah, this software simulation focus. I know. Okay, so we have now, in order to simulate a negative lens, what do you have to do? You have to switch. Let's see. No, doesn't work. That here. Oh, what a shame. Oh yeah, we have to switch the focal point, right? Here you go. That's how you do it. Right? For a negative lens, the focal point is on the other side. Here you go. And all these images will be virtual, no matter what's the position of the object. Okay? Will be upright, virtual, and smaller. Just like we get for the convex mirror. Okay, let's okay, I'm going to copy and paste what those results that we saw. Okay. And here you go. Convergent lens, divergent lens. Let's convergent lens. Okay, object placed in front of the lens at a position greater than 2f. Light ray coming from the tip of the object and parallel to the axis is refracted towards the focal point. Passing, right? Unrefracted. Let's see if I can put it unrefracted. Object real, image is real. Inverted and smaller. Object placed in front of the lens at position between f and 2f. Okay. Object inverted and image object is real, image is real, inverted and larger. That's for a real object. We can also have a virtual object, but we're not going to cover here in this course. Object placed at distance f in front of the lens at the focal point. Focal point f prime. Image form is improper. Object placed at distance less than f. Light ray coming from the tip of the object. Image is formed in front of light ray. Image is formed in front of the lens, virtual, upright and larger than object. And for the divergent lens, we don't have all that complication, right? We have much simpler divergent lens. Everything that I did there is now documented here. Don't forget, very important here, for divergent lens, the focal distance is negative. Okay? It's going to become important. Convergent lens, focal distance is positive. It's going to become important when we start dealing with the formulas. And here we go. The equations of the scene lens. Equations of the scene lens. Of the scene lens. Scene spherical lens. It's going to be exactly the same as that for the mirror. Okay? The same arguments, the same geometrical arguments that we used, that can be used for mirrors to find this equation, can also be used for lenses to find this equation. So it's not difficult to memorize that, right? There's nothing new here, right? And that what, let's take a look also at the book. Oh, and by the way, let me give you a link for the simulation. There are more simulations out there. This is not the only one that you're going to find out. Simulations simulation for lenses in the internet. Simulation links. Here you go. That's the simulation link. The internet. $9.56. Okay, so let me take attendance here. We have 6 students. Roster. Okay, lecture attendance. Today is the 6th of May. Jacqueline, are you there? Okay, thank you, Jacqueline. Next is Sky. Thank you, Sky. Next is Ashley. Okay, good. Next is Corina. Corina is not here today. Next, Norberto. Norberto disappeared, unfortunately. Vanessa.
Here.
Thank you, Vanessa. Yorgo.
Here.
Next is Giselle. Giselle is not here either. Paul Zapata. Okay, so that's 6 students. Yeah, we do have 6 students. 9:58 right now. Any questions about that? About this material? Break. 10 a.m. to 10:15 a.m. Okay. Let's go a little bit. No questions? If you don't have any questions, let's, see you at 10:15. Okay, let's go a little bit longer this time, 17 minutes. And I see you soon. Stop sharing. I'm back here. And what I want to show you, see here, I want to show here this chapter, right? So you can be located. We go, index of refraction we covered in the lecture. Okay, Snell's law we covered in the lecture. Total internal reflection was the next topic. There you go. We skipped polarization. There you go. We skipped polarization for now. That's total internal reflection, still total internal reflection. So if you go, we skipped this one, this section. We covered dispersion of light. We covered lenses. Okay. Here you go. Double convex, planar convex meniscus, they call it convex concave. I call it convex concave, they call it convex meniscus. Planar convex, right? And diverging. Formation of image by lenses. Okay. I cover that as well. Notice that the book is using a slightly different notation. They're calling F and F here instead of F prime and F. It varies from reference to reference, okay? Some references that do exactly what the book does, but other references, they do exactly how I do. use the IF and F prime. Okay, converging lens, diverging lens, image formation by converging lens. Okay, here you go, real image. Okay, the image of a diverging lens is the magnification is less than 1, right? Whereas if you use a converging lens as a magnifying glass, the image is virtual as well, but it appears enlarged. Same lens equation and the magnification equation, right? And the same lens equation and the magnification equation, which is exactly the same equation of the mirror right in here. Thin lens equation. But don't forget, it's a thin lens. If the lens becomes, thicker, then we have to use a slightly different formula. Thin lens equation. F is positive for converging lens. F is negative for diverging lens. D naught is positive, the object is to the left of the lens. And D naught is negative, is the object is to the right of the lens. It's possible to have a virtual object, okay, but we're not going to cover that here. So let's stick to the simpler case here, in which the object distance, in which the object is a real object. Image distance, this one you have to know. Di is positive for real image, Di is negative for virtual image. M is positive for an upright object, M is negative for an inverted object, inverted image. Virtual image form, you go the geometrical optics procedure, right? That I'm insisting here. Collimated light ray passes through the focal point, light ray that passes through the center. And let's see, lens combination. We still haven't covered lens combination. I'm going to skip this one for now. I'm not going to get into the human eye, okay? Since it's important here for you. And this one right in here. We covered that. We covered that. I am both facing what we covered, what we covered, right? So, am I recording? Yes, I think so. Yeah, we are recording it. And then the human eye. What you have to know about the human eye is that it behaves just like a convergent lens. Most of the converging of the light is done by the lens in the eye. But then there are other layers also of the eye that also does some job in converging the light, okay? It's not just the lens of the eye, but then there are other features in the eye, like the cornea, that also contributes to the refraction of the light that goes through the eye. But a very good model of the eye is that the lens of the eye is the one that does most of the refraction, okay? So the human eye behaves just like a convergent lens. Most of its refraction, not all, I'm going to put it here, not all, is done by the lens in the eye. So And then the human lens has the capability, not this capability, but the capability of changing its focal length. Okay. The lens of the eye is flexible enough, to be bent to different, flexible enough to be bent by the muscles in the eye into different radii of curvature, okay? Into different radii of curvature. If an object is very close to the eye, so at this very moment, look at me here, right? Look at me. At this very moment, my finger is very close to my eye, okay? In order for my eye to see this, my finger very clearly, the muscles in the eye must increase the curvature, the radius of curvature of my lens, okay? Now, when I place my finger very far away from my eye, then the radius of curvature of the lens of my eye becomes a little flatter, okay? So regular lenses out there cannot do that. Regular lenses made of glass and plastic, they're too rigid for you to change the radius of curvature, their radius of curvature, okay? Compare this to regular lenses that are sold in the market, right? These lenses are made of glass and plastic, and they are too rigid for us to change their radii of curvature. Unlike the human eye. Okay? Now we're going to talk about the adverse conditions of the human eye. Nearsightedness, and farsightedness. Farsight. Yes. Near sight and far sight eyes. Near sight, let's see if we can do that. Okay, near sight and far sight eyes. Okay, let's do this way. Nearsighted and far-sighted eyes. Okay. Okay. In a nearsighted eye, the image of the object is formed before the retina. Okay. Why is that? Why does it happen? Well, this happens because as you grow, right, for some reason, the eyeball becomes stretched or longer. And the lens of the eye is not powerful enough to focus the image there at the retina. Okay, for this reason, in a nearsighted eye, we can only focus the light on the objects that are closer. Let's see if I have a drawing here to help you out understand that. Okay, here you go. Normal eye. Here's the lens, right? And if you're looking at an object that's far away, the image is formed exactly at the retina. But in a nearsighted eye, what happens? The eye gets too stretched, just like my case. I'm a very nearsighted person. These lenses that you see here, my eye is very extended. When I go to the doctor, he tells me he can see that my eye is very elongated. So when you become nearsighted, what happens? The image is formed between the lens of the eye and the retina. And because of that, the image is not in good focus, okay? And there is a way to correct that. There's a way to fix that. And that's something that we knew for a very long time, I would say even 500 years. Let's see when they invented this eyeglasses, right? When they invented the eyeglasses, let's see. Prescription history, Wikipedia. When did they invent the eyeglasses? I think it was around 1500. Maybe it was earlier than that. Glasses, history, right in here. Precursor. Scattered evidence exists for use of this. Oh, in Greek and Roman times. It's not just in 1500s. It was way back in antiquity, right? It's scattered, but it's scattered evidence exists for use of visual aid devices in Greek and Roman times. Most prominently, the use of emerald by Emperor Nero, as mentioned by Pliny the Elder. Okay, the use of a convex lens to form an enlarged, magnified image was most likely described in Ptolemy optics. Wow, back in the Claudius Ptolemy. This guy, 2nd century book. Huh? So he was around 200 AD. This book was published around 200 AD. Here you go, 160, during the 160s. Okay, it was in antiquity, which survives only in a poor Arabic translation. Poor Arabic translation. What a shame, right? Ptolemy's optics, with the fall of the Roman Empire, right? Many things got lost. And with the rise of the Arabic civilization, unfortunately, they translated it to Arabic, but the translation was a poor one. Okay, an Arabic based on Arabic translation was presumably based on the Greek original. So the original was in Greek. So let's go back. Convex lens, Latin translation of Ptolemy optics, and became available in Europe in the 12th century, coinciding with the development of reading in stone. What reading in stone? Oh, here you go. That's what a reading stone is. Approximately hemispherical lens that can be placed on top of text to magnify the letters so that people with presbyopia can read it more easily. Reading stones were among the earliest common uses of lenses. Okay, this guy here, portrait of Cardinal Fernando Niño de Guevara, but it was circa 1600. So here you go. We have eyeglasses that looks like modern eyeglasses of today, right? Detail Dominican Cardinal, 1300. Painted. So he's also using an eyeglass. That's 1300. That's a modern eyeglass, of course. Okay, mentioned using optics to read the smallest letters at incredible distances a few years later. Okay, Roger Bacon is also known. So it looks like things start to happen in the 1200, right? They used to have visual aid devices for whoever was nearsighted or farsighted, but the evidence is only scattered. There are claims that a single lens magnifying in China during the Northern Song Dynasty invention. The earliest recorded comment on the use of lenses for optical purpose was made in 1268. Okay? 1268. The first eyeglasses were estimated to have been made in central Italy. Central Italy, remember, at that time, during the Middle Ages, the Italian city-states were the superpowers of the time. Okay, and during the Renaissance, those guys were doing magnificent things, okay? Most likely Pisa by about 1290. In a sermon delivered 23rd February to 1306, the Dominican friar Giordano da Pisa, all right, wrote, "It's not yet 20 years since there was found the art of making eyeglasses which make for good vision." 20 years. Okay, and it's so short at the time that this new art, never before extant, was discovered. I saw the one who first discovered and practiced it, and I talked to him. Okay, Giordano's colleague. Think about that. You know how people would be able to live with a nearsighted eye, especially me. Imagine if I were living during antiquity and I had this lousy eyes of mine that's highly nearsighted. How they would be able to live normal lives, right? And it took a kind of a long time to come up with an eyeglass. So let's go back here, right? A little bit of history. And how do we correct a nearsighted eye? A way to correct the nearsighted eye is to make the focal distance of the overall image longer, right? We want to get the light rays to be focused at the retina. So consequently, we have to make the overall focal distance of the eyeball longer. And how do we do that? We do that by using a corrective negative lens, okay? But it must be the right lens, right? This lens that you see right now that I'm holding right now, that I use right now, is a negative lens that diverge the light rays. When you diverge the light rays, you increase the focal distance of the set lens in the eye and lens outside the eye, okay? So that's how we correct for nearsightedness. And then, nearsightedness usually happens. In my case, I became nearsighted when I was 17, 18 years old. Now I am 60. Okay, now I am 60. So it's common for people to become nearsighted at this age. And I had friends that, since much younger than me, that they already use eyeglasses. Now, the next type of eye, which is a farsighted eye, is an eye become farsighted when you age. As you get older and older, you are going to get a farsighted eye, and you're going to need to use reading glasses. A farsighted eye is exactly the opposite of a nearsighted eye. The eyeball, instead of becoming stretched, it becomes compressed. And the image, instead of forming exactly at the retina, where it's processed and sent to the brain by the optical nerve, right? The image is formed past the retina. So what we have to do? We have to shorten the focal point of the eye and the external lens set. How do we do that? We do that by using a converging lens. Make sense? When we use a converging lens, we are shortening the focal point of the lens in the eye with the other lens. Okay, that's what you have to know. And I'm going to copy, and I'm going to, here you go, farsighted eye. Here you go. Nearsighted eyes. In nearsighted eye, the image of the object is formed before the retina. This is because the eyeball becomes stretched or longer and can focus only on the objects that are closer. Farsighted eye. In a farsighted eye, the image of the object is formed after the retina. This is because the eyeball becomes shorter and can focus the object and can and consequently, the image is formed. The image can only be formed. The image can only be formed after the retina. Okay. This is because they're about, and consequently, and the image can be formed only before the retina. Okay. We call the behavior of a positive lens. The further the object becomes from the lens, the closer its image is formed. The closer its image is formed to the focal point, not from the focal point. The closer an object becomes from the lens, the further its image is formed from the focal point, right? This is better. To correct for this condition, a nearsighted eye must wear a negative lens, and a farsighted eye must wear a positive lens. But must be the right negative lens, must be the right, but don't forget, it must be the right positive lens, but it must be, but in both cases, it must be the right negative and positive lenses. Okay? That's why you go to the eye doctor. The eye doctor makes measurements of your eyes, and they can even see the image forming in your retina. Okay? Farsighted eye, a nearsighted eye. You can even see the image forming in your retina. Now here go how the eye, the anatomy of an eye, right? But like I said, most of the refracting power of the eye comes from the lens, but everything else also contributes. The cornea contributes, the aqueous humor contributes, okay? And there is more. Not only you can change the radius of curvature of the lens here using the muscles in the eye, the ciliary muscles, okay? But you can also allow more or less light to go through the eye by, by making the pupil, right, smaller or larger, okay? So it goes anywhere between the diameter of the pupil, for instance, that black, the black spot in the middle of the eye can vary anywhere between 2 to 7 millimeters, okay? The brighter the light is, the smaller the pupil becomes. So let's write that down. Okay. The lens, I think I wrote that down, right? Yeah, I already wrote that down. In addition to change the eye the lens curvature, the curvature of the lens. So that are the ciliary muscles. The pupil of the eye also can be changed in diameter to let more or less light pass. Its diameter can be anywhere. That's according to the book, okay? Between 2 millimeters. And the book says 7 millimeters, but I have seen other books there that says to be 9 millimeters, okay? The book for some reason says, let's take a look. Pupil diameter. Largest diameter. Pupil size. See, this reference here is saying 8 millimeters, but I have seen references that points all the way up to 9 millimeters for the diameter of the eye. Here you go. See that? Look at this eye. Completely huge, right? The pupil is so large that's almost covering the whole iris. Okay, look at the pupil size. That's when they put those little eye drops, right, on you, that the pupil becomes this size. When they do that to me, man, I look in the mirror, it scares me. See my lens, my eye just like that, covering the whole iris. Here you go, mydriasis. What's mydriasis? The dilation of the pupil, usually having a non-physiological cause or some type of physiological pupillary response. Non-physiological cause of mydriasis include disease, trauma, or the use of certain types of drugs, like your doctor do when you go to the optician, right? They dilate your pupil. But in this case, it's more like a disease, right? Disease, trauma. Okay. Pupil, here you go. Function, here you go, the eyes, right? The length of the eye, the pupil, sclera, ciliary, body, iris, the cornea, aqueous humor. So the cornea has some refractive power. The aqueous humor also has some refractive power, okay? Going back to the book. And you go. The lens is connected to ciliary muscle by suspensory ligaments. We'll see shortly how the shape-changing ability of the lens affect the focusing ability of the eye, okay? So depending again on the curvature of the lens, you can change the focal point, the focal distance of your lens, the length of the eye. Okay. Nearsightedness. Okay. Here you go. Negative lens, focusing the image at the retina. And here's the case of individuals that cannot distinguish colors, right? But we are not covering that. Okay, and let's see, yeah. Okay, and we can, let's see if I can get something else here. So that's what I want to cover for this chapter for now. Okay, if we have time, we're going to come back to lens combination and the other topics here. Compound microscope, telescope, okay? But at this point, let me get the other notes. Any questions about that? I want to get, let's see here. 2023 spring P07. This one here. Oh yeah. So, and what I want to do now, chapter 26. What I want to do now, I want to skip chapter 27, and we are going to go to chapter 28, okay? So, notes 24 right here. Skip. Lens combination, skip, right? Skip, and skip, and then the human eye. Like that. Now, what we want to do is a special relativity. Chapter 28. Okay, this is the physics. What we are going to do from now on is going to be the physics of the 20th century. Special relativity, the physics of the 20th century. So for most of the things that we have covered here are just knowledge that or known all the way down until the end of the 19th century. But now we are going to start talking about something special, the special relativity, which was developed by Albert Einstein. A special relativity was formulated by Albert Einstein in the first years of the 20th century. Okay. Well, what Einstein, discovered was something so simple and yet so difficult to understand. That something that escaped the common sense. Okay. What Einstein discovered was something that was that is not was but is very simple to formulate, but very counter something that is both very simple to formulate and yet very counterintuitive as well. Intuitive. It was so counterintuitive. It was so counterintuitive that it took a long time for the scientific community to accept as a fact. Okay. So what are the laws of physics so far, right? Accept it as a fact. Okay, so here you go. Laws of physics so far. Newtonian mechanics, 3 laws of motion. In reality, there's 2 laws, plus the law of gravitation, right? In reality, it's only 2 laws. It's only 2 laws because the first law is just a consequence of the second, plus the law of gravitation. In thermodynamics, 4 laws, zeros, first, second, and third laws. Electromagnetic theory, we have 4 laws as well. Gauss's law for electric and magnetic fields, Ampere's law, and Faraday's law. Okay, and the ray optics, the law of least time. In the case of relativity, in the case of special relativity, later on, Einstein developed the theory of general relativity, okay? Which is, I want you to pay attention here, special relativity and general relativity. Okay? Relativity, comma, its laws, 2 laws, apply only to inertial referentials. Okay, what's inertial referentials? Or referentials that are moving with constant velocity. Inertial referentials. See here, constant velocity. Now, do you see the difference? I'm going to put a little table here, not exactly a table, but special relativity versus general relativity. Okay. Constant velocity. Constant. That's the difference between special relativity and general relativity, okay? It's constant velocity. Variable velocity or accelerated variable velocity or accelerated motion. See the difference? That's a general relativity. We're not going to cover general relativity, but I want you to understand why it's called this. One is called special relativity and the other is called general relativity. Because this one is applicable only to constant velocities, to frames of reference that are moving with constant velocity. Whereas the other is more generic, is more general, and applies also to accelerated frames of reference, accelerated motion / accelerated frames of reference. That's the important. So Einstein proposed 2 postulates to explain the universe. Einstein. Proposed two postulates or laws for his special theory of relativity. The first one is the relativity postulate, and it's very simple. Okay, it's very generic. It's we all assume that it always apply, not just in special relativity, but also in Newtonian physics. The laws of physics are the same in every inertial frame of reference. That's easy. That would be easy to accept at that time. What was not easy to accept at the time was that the speed of the light postulate was that the speed of the light in vacuum measured with respect to any, very important, any inertial frame of reference will always be 300,000 kilometers per second, no matter how fast the source of light and the observer are moving relative to each other. You know, that's counterintuitive. That's counterintuitive. And I can illustrate that. Not only is difficult to see, but it's also is difficult to accept, okay? It's difficult to accept because now it is a different, what he's proposing, what Einstein proposed at the time, it was a different way of thinking. We can go back here. So in the second postulate, Einstein was proposing a completely new way of thinking. Okay, that's why it was so revolutionary. And I'm going to illustrate for you. Close that. Relativity, here you go. Chapter 28. Illustration of relativity, second postulate. I'm going to illustrate the second postulate. Okay. So consider that we have a laser source. Let's see, here you go. I have a laser right in here in my hand. Laser pen. Doesn't have to be a laser source, can be any light source, laser or light source. Or light source. They don't have to be necessarily a laser. And here I'm representing referential A. And this referential A is at rest with respect to us, okay? And this, I'm gonna step by step here. I'm going to do like that. Here you go. Let's do step by step, right? The referential A. Referential A at rest with respect to us. Okay, I labeled it A. And now what I'm going to do, I'm going to put the laser source in this referential. Laser source, laser or light source. I'm going to turn on my laser. Turn on my laser. Here's the laser beam. And then I'm going to come up with a detector as well. A detector that's going to measure the speed of the light. the speed of this light beam. It's possible to do that. Okay. And both this detector and the laser, they are at rest with respect to referential A, which is at rest with respect to us. Light source, I'm going to write that down here. Both the detector and the laser are at rest with respect to referential A. Okay. Do I need anything else? What happens? You know, detector measures speed equal to 300,000 kilometers per second. That's how the story goes, right? So here, referential A, laser or light source, laser beam, and then we come up with a device, a contraption that's capable of measuring the speed of the light of this beam. Both the detector and the lasers are at rest with respect to referential A. Detector measures a speed equal to 300,000 kilometers per second. Well, that's simple enough, right? What's not simple enough is what Einstein proposed in his postulate of special relativity. Now, instead of getting my detector at rest with respect to the laser, and I'm going to put my detector in a referential B moving towards the laser beam, the laser source. Okay. Now this detector is approaching at a given velocity, a given speed, VBA, velocity of referential B with respect to the referential A. Both devices at rest with respect to different inertial frames of reference. Laser is at rest with respect to this referential frame. The detector is at rest with respect to this other referential frame. Notice that I put different colors, right? Red here and black here. So I give an instant of time. The detector is here. A little bit later, the detector is going to be a little bit closer. Okay? Because it's moving towards the laser source. Okay, and that's where relativity diverges from mechanics, Newtonian mechanics. Newtonian mechanics would expect that this detector would measure a speed of the light as being 300,000 kilometers per second plus the speed of the referential frame B. Okay? But that's not what Einstein stated. Einstein stated that in reality, what this detector is going to measure is still going to measure 300,000 kilometers per second. Okay? That's what the second postulate of Einstein is all about. Do you see how counterintuitive it is? We're so used to think in terms of relative velocity. If you're approaching an object, the relative velocity is going to be higher. If you're moving away from the object, your relative velocity is going to be less, but not when we are dealing with very high speeds compared to the speed of the light. Okay? And same thing here. Okay? So if the detector is moving away from the laser source, no matter what, the detector is still going to measure 300,000 kilometers per second. balls at rest with respect to their respective, right? To their respective and different inertial frames of reference. That's better. This laser source is here. Okay, here you go. Both devices at rest with respect to difference. But now what am I doing here? It doesn't matter if it is the referential B that's moving towards the laser or the laser moving towards the detector. It's still going to be 300,000 kilometers per second, not 300,000 kilometers per second plus VPA. Okay, and here you go, receding, right? It's still 300,000 kilometers per second. That's the central idea of special relativity, the theory of special relativity of Einstein. Okay, and it is very difficult to accept that, very difficult to understand it. I'm gonna just go. We have 5 different situations that I illustrated. Okay, so here you go. The second postulate can be illustrated the following way. If you have a laser pointer and a detector to measure speed of the light, if the detector is at rest with respect to the laser point, the detector will measure a speed of 300,000 kilometers per second for the laser, right? If the detector is moving towards the laser point, the detector will still measure 300,000 kilometers per second, and so on. 5 different situations. And 11:10 right now. Any questions about that? Remember that, okay? Don't forget. It's very difficult to picture something like that in your mind at first time, but that is exactly how the universe works. But this happens only for the speed of the light, and for regular objects it also somewhat happens, but it's something that we're going to cover very soon. Okay, let's take a break here. Break 11:10 a.m. to 11:25 a.m. Any questions? So I see you in 15 minutes. I am back here. Let's take a look at the screen. Here you go. Here's the book, right? Events and inertial frames of reference frames. Okay, and then the postulate of special relativity. We are writing here. We are writing here in the postulates of special relativity. And I want to spell out every section here. There are very nice videos about special relativity, okay? One of them that I like the most, unfortunately, the quality is not so good. The one that I find in the YouTube is the Mechanical Universe, the video series, the Mechanical Universe, on special relativity is, you can find it in YouTube. You can find it in YouTube. A very good explanation And I highly recommend them. I recommend you to watch it outside, watch it on your own. The only problem that I don't like about this version of YouTube is the poor quality in the image. Unfortunately, they posted a video that is very poor quality there in YouTube. And I'm even ashamed of showing that to my students. I used to show that to my students every time that I used to teach. But I had, at the time, I had access to a very high quality DVD that I used to show. I like it to show that to my students. We go, mechanical universe. So let me show you the mechanical universe. YouTube. See, that's episode 1. You don't want episode 1. You want the later one on special relativity. See, that's episode 42. It starts at episode 42. Okay, and Lorentz transformation. You go relativity, the mechanical universe. This one here. Well, begins when you understand that the strongest energy. They don't say which video is this one, but they have very good animations that explains very well how. Let's watch. Let's see. Let's watch this one. Yeah, this one here, unfortunately. Yeah, what you have here is just it's not the full video, okay? So, but you can check the other ones. This one here seems to be complete. Okay, and here's another one too on a special relativity. It's more than one video that they have. They have a special relativity 1, the Michelson-Morley experiment. So at least 3. You have at least 3. Okay, and so on. Okay. And what I want to do, I want to spell out the sections of the book that we are going to cover. (28.1) events and inertial frames of reference. 28.2, the postulates of special relativity. 28.3, the relativity of time dilation, and that those are one of the consequences of the postulate of special relativity. The relativity 28.4, the relativity of length contraction. 28.5, we have relativistic momentum. 28.6, the equivalence of mass and energy. This is the chapter where you are going to see that famous equation of Einstein, E equal to mc squared. And 28.7, the relativistic addition of velocities. Okay, we already covered those two here. And let me tell you what are the consequences of those two postulates. The consequences of these two postulates are overwhelming. Okay. One thing is to say that the speed of the light is the same, irrespective the relative their irrespective to their relative velocities. Okay. Another thing completely different is to work out the consequences of these two postulates, especially the second one, because the first one is kind of harmless. The consequence of the second postulate, that is something that is completely difficult to believe. Okay, and I'm going to spell out some of the consequences of the second postulate, and then we are going to work out the mathematical proof based on this postulate, and on the top of that, I'm going to provide you with experimental evidence of what actually happened, that something like that happens. Okay, so here you go. Consequences. Second postulate. A very important consequence. Some of them being the time dilation. Time is observed to flow differently between two inertial frames of reference, from one inertial frame of reference to another, from one inertial frame of reference to another. Okay. In other words, a clock in your inertial frame of reference will run faster than another clock. It's not just the physical clock, but it's also the biological clock run faster than another clock attached to inertial frame of reference that's moving either towards or away from you, right? So someone in the other inertial frame of reference is seen to age more slowly. Okay, and that has been verified experimentally over and over again. That has been verified experimentally. And then we have the other important consequence, which is the length contraction. The length of an object in a second inertial frame of reference is measured to be shorter. So if you are on Earth observing an approaching spaceship moving at very high speeds, close to the speed of the light, close to the speed of the light, right? The length of the object inside the spaceship, and the spaceship itself, by the way, and the spaceship itself, by the way, are measured to be shorter if compared to a standard. Okay, so a standard meter. So the way it works like that, you have your meter, your ruler, right? Your 1 meter long ruler here on Earth. And the other guy, the other spaceship also have the same meter ruler that in his spaceship. If I observe here from Earth the meter rule and measure the length of the meter ruler in the other ship, I'm going to measure it shorter. This is a fact as well. Are measured to be shorter if compared to a standard meter, but are measured to be shorter by the observer on Earth. On Earth. Okay? So those are two consequences difficult to accept. Difficult to accept. And that's why Einstein, when he won the Nobel Prize in physics, he didn't win the Nobel Prize in physics because of special relativity, even though it was completely a very important contribution. One of his most important contributions was special relativity and general relativity. He didn't win this Nobel Prize because people wouldn't believe at that time. He won the Nobel Prize for other things, for other reasons, okay? For other reasons that were also important. That were also important. If we go to the internet, you're going to see the citation. Okay, you know, Einstein, Nobel Prize. I'm gonna Wikipedia. You're going to see there is no mention of whatsoever of the special relativity. Albert Einstein here. Let's see here. Nobel Prize. But only a vague mention that was all other contributions. Let's see. Nobel Prize. Nobel Prize. He was awarded 1921 Nobel Prize. Okay, he's awarded there by the Swedish Academy of Sciences. Let's see, in the novel, at this point, some physicists still regarded the general theory of relativity skeptically, and the Nobel citation display a degree of doubt even about the work on photoelectricity that it acknowledged. So the Nobel Prize in Physics made reference to Einstein's work on photoelectrons. Okay, photoelectricity, his work on photoelectricity. He did not assent to Einstein's notion of particulate nature of let's see. Let's see the full mention. I want to for his contributions. Let's see, banquet that year participated in Nobel Prize ceremony. Doesn't look like they have it here. We have to go elsewhere. Let's see here. Nobel Prize in Physics. Background, nomination and selection, medals, diplomas, award money is $1 million. You know, oh, $1.5 million, almost $1.5 million. Little every passing year, they increase slightly. Okay, the value of the Nobel Prize ceremony. See also this. Let's see here. Let's take a look at this one here. Statistics. Einstein. Okay, here you go. See, this guy here, Röntgen, in recognition of extraordinary services he has rendered by the discovery of remarkable rays subsequently named after him, was the X-ray. And then that's what I'm looking for. And let's take a look at Einstein. Albert Michelson, Marconi. Marconi was a very wealthy individual who, by the way, stole the ideas of Tesla, Nikola Tesla, and he ended up winning the Nobel Prize. Tesla got mad at Marconi because of that, and he went to sue Marconi for that. Marconi used his discoveries, his inventions, and because of Tesla's inventions, Marconi ended up winning the Nobel Prize, something that Tesla himself deserved. What about, where is Einstein here? Einstein, okay. For his service to theoretical physics, and especially for his discovery of the law of the photoelectric effect. No mention whatsoever of the special theory of relativity, nor the general theory of relativity. The whole scientific community was very skeptical about the special theory of relativity, and now we teach that to our students. Only mention here they make is the photoelectric effect. That's it. Okay? The photoelectric effect, which is the ejection of electrons by light. Okay, the photoelectric effect was discovered in the 19th century by Wilhelm Hertz, and observed, right? Discovered and observed experimentally, and only afterwards Einstein was able to explain that. Let's take a look at photoelectric effect. We didn't cover that. Unfortunately, we didn't cover the photoelectric effect, the history of photoelectric effect. Let's say history, 19th century. I want Heinrich. Hey, it's not a Wilhelm. It's Heinrich Hertz, 1887. Okay. So it took more or less 20 years for Einstein to explain this effect that Heinrich Hertz discovered. That is the historical background. Lens contraction, what else? Relativistic linear momentum. We have seen the linear momentum in physics, right? And the linear momentum is written in terms of mass times velocity. In special relativity, this relationship is slightly different. In special relativity, this relationship ends up becoming slightly different. Okay? Another important consequence is that the relative velocities between objects is not the straight vectorial summation. Okay? Are also different, not slightly different, like let's put different, okay? It's no longer the straight forward vectorial summation. Okay? And then we have this relativistic energy that he derived as well. Okay. That's what the book, the equivalence of mass and energy. Okay. An object, a mass has some energy on it, and the energy also can be converted into mass. A massive object has some internal energy that is given by this equation. It's a huge amount of energy because we're talking about a large number, 300,000 kilometers per second squared. And that was the beginning of the atomic weapons and the atomic and nuclear energy. Einstein predicted the huge amount of energy that can be generated by a mass. Okay? So those are 5 important consequences of that simple postulate that we saw. We have 15 more minutes to go. And what I want to do that, I want to introduce you to the light clock. I'm going to introduce you to the light clock. Think about a timepiece. Think about a timepiece. Not just your regular mechanical / electronic timepiece, but a timepiece that uses the speed of light to keep time. Okay? This is a very nice thought experiment that we can do to derive the consequences of special relativity, especially the case of time dilation. So try to visualize in your mind how this light clock works, okay? Here you go. We have the light clock is illustrated right in here. Right in here. It's made up of two mirrors, one at the top and the other at the bottom. And a photon, or let's say a very short beam of light moving back and forth because of those reflecting surface. Can you visualize that? And that's when the mechanical universe, that's where the mechanical universe excel in illustrating. Think about again. You know, every reflection here of the light clock is a tick and tock, tick tock, tick tock. The light clock, the two mirrors of the light clock has a distance d. The photon of light has a speed of 300,000 kilometers per second. Okay. And now we have two different referentials. A referential A, that's the black one, and a referential B, that's the red one. I'm gonna make it a little bit thicker. Both thicker, let's see. So you can see it more readily. Okay. Make it a little bit thinner. Okay. And this, what you see right in here is an observer illustrated by a big eye, right? Here you go. The eye and the pupil there. That's another observer. The observer that is at rest with respect to us, and the observer that's moving with a constant velocity. Remember, this is a inertial frame of reference. At time t equal to 0, the clock is in this position. A little bit later on, the clock moved away, and so on. Okay? 3 frames, right? And I'm going to go. Here go the black and the red one. Okay. So here you go. That's another illustration of the same thing, right? So here I picture the clock as black, as being black. But look what the observer in referential A sees: the path of the light beam, of the photon, of the light particle. An observer that is in referential A, I'm not going to get his eyeball again. Back here. We'll see the path of the light clock undergoing this path, right? A longer distance, traveling a longer distance than this other observer here. Okay? He sees a longer distance because this clock is moving with respect to this guy, but not with respect to referential B. With respect to referential B, the distance the light travels is shorter. Okay? So if this a full oscillation is going to be twice d here, a full oscillation here is going to be this distance plus this distance. And you can calculate that. Okay? So I have here, I'm going to document here for you. The height of the, not the height, but the distance, right? Okay, the distance, the light clock, okay, let's write that. The light clock is made of two mirrors facing each other and a photon of light bouncing back and forth between these two mirrors. The distance between the mirrors is d. The speed of the light is c. Is c. Speed of referential b is I'm gonna put it here, God. I'm gonna use the same notation that I use in my physics 6 course. Velocity of b with respect to a. Okay, in case you don't remember, I'm gonna spell that out here. Velocity of referential b with respect to a. Both referentials have exactly the same clock, light clock. In referential, let's see. I'm gonna take this one out for now. In referential B, the period of the light clock measured by the observer in B is, right? And then we can solve it. Here's the period of the clock. But remember, as measured by the observing B, I'm going to boldface and italicize. However, for an observer in referential A, the period of the light clock in B is going to be different. It's going to be different because the speed of the light is the same, no matter the referential. That's second postulate. Okay, 1156. So going back here, right? We have D here. We have VT here. Make sense? I'm going to copy that and paste in there. So you can have as a reference for you. Okay, this distance is D. This distance is VBA. Okay, and from here to here, it takes an amount of time equal to the period of the clock divided by 2. Make sense? Okay, so total length, total travel length above is twice the diagonal, twice, 2 times the diagonal, okay? Diagonal, right? And this one is going to be 2 times the square root. Let's see. Equal square root right here. Okay. This distance, right? dBA times T period as measured with respect to referential A. C stands for clock, okay? Divided by 2. And okay, so that's going to be this length plus this length. It's going to be this length plus this length. And this length is going to be this square root alone. I put lowercase d, right? Did I put? Yeah, I used capital D here. This one is supposed to be capital D as well. And one more thing, one more student. Equals auditado. And then what else? So that's going to be, let's see, the speed of the light is square. Oh, it's going to be equal to the speed of the light square times TCA square. Okay, period as measured by the period of the clock, C as measured by an observing referential A. Okay. It's better that we, let's see. When we solve this equation, let's continue going this way. Okay, so we go ahead and work out. Oops. I'm gonna pass this 2 to the inside, okay? When we pass to the inside, we end up with this velocity square. Oh, not this one. VA. We have this time square, the period as measured by the referential. We have 4 here because we're squaring, right? And then I gotta put an equal sign as well. The 2 that is outside is going to become 4 on the inside. And it's going to become 4 here as well. And then we do not have the square anymore because I already expanded. Well, 12:02 already, yeah? Okay, let's stop now. But what I want to do, I want to solve for when you do everything, when we invert, we want to find this guy here, the period of TCA. Okay, what we end up finding is that the period as measured by an observer in referential A is going to be different from the speed measured by referential in by an observer in referential B. And it's going to be according to this factor, okay? Gamma factor. And now we can stop it. Gamma is exactly this ratio that you see right in here, okay? This V that you, the V squared that you see right in here is this VBA. Velocity of B with respect to A. Okay, it's 12:03, 03. Do you have any questions? And that's what I mean by time dilation. I'm going to elaborate a little bit more next time so you understand how this equation behaves, okay? So no, there's no questions. We can stop here right now, and I see you on Wednesday. And don't forget, the exam is next week. Okay? See you. You too, Vanessa. Thank you. And let me see here. Nicholas, are you there, Nicholas? Oh, yeah, here you go. So you're taking physics 38 with me, right, Nicholas? Okay, and so do you have any questions for the exam next week? Okay, that's good. So just for the attendance credit, right? So let me just show you the syllabus. Did you talk to the other students about this office hours meeting? Did you manage to tell them about that? Let's see, this one here. Syllabus must be this one here. No, yeah. Oh, okay, that's good. What about here? Gosh. Have to make, okay, let's see. Let's review what we have here, right? The syllabus right here. Okay, today is May 6th. And, oh, wait a minute, what's going on here? Oh, yeah, that's right. The 15th is going to be next week, right? The 13th is going to be Monday. The 15th is going to be Wednesday. That's going to be the third partial exam. And those are the chapters. Let me get you here. The attendance. Hurtado, Nicholas. Ah, okay. Today is the 6th. Here you go, Nicholas Hurtado. So I gave you the attendance. How's the homework? How are you doing the homework there? Oh, I see. You haven't started yet? Didn't you do anything so far? Anything so far? Any of the chapters? 29, 31, right? We started. Let's see, we started with 29. Okay. And what about the other chapters? Did you manage to do the homework for the other chapters? 21 through 28? Ah, okay. Okay. So when you mentioned about starting the homework, you mean the homework for chapters 29 to 31. That's what you mentioned. Okay, that's good. Okay, so as practice, right? Okay, yeah. Yeah, that's a good way of approaching it. Let's quit it. I quit it here, and I'll save it here. So let's see, Hurtado. Yeah, okay. So you came on the 24th, and I come back. Okay, that's good. I will close it here. Can you please send me a transcript? Okay. Okay. Um, yeah, pretty good, pretty good. Okay. Okay, so let's see. I'm going to switch here to a different self login. My Zoom. Okay, so lab report. How was it? I had a question about an assignment I saw on Canvas. There was a blank assignment that was titled lab report. Oh yeah, you don't have to worry about that. I'm using that just as a placeholder for the grades. So don't worry about that. Okay. It's like I said, it's just a placeholder so I can display your grades in real time. Okay. So don't worry about that. Your lab report is whatever you're doing in your lab with the other instructor. So if you go in your grade, right, you're going to see that you have like a real-time grade of yours, and that was possible because I put that so-called assignment, right, lab report in Canvas. That's why. So don't worry about it. Let me